Hello. I'm sorry I was rushing a little bit at the end of the last video, but I was running out of time. I have a 15-minute limit. So what I was saying was that here in this last part, the distance away from the origin is getting smaller and smaller from me, so it's coming towards me, and it's changing gradient. Here there is a very sort of, well, here there's a gentle gradient, and then here it already starts getting very, very big. So if the gradient is small and then big, it means that the speed goes from smaller to big. So the speed is increasing, and therefore we call an increasing speed, we call it an acceleration. Okay, and it's a positive acceleration because the speed is increasing, even though the gradient is negative and coming towards me. The speed goes from small gradient to big gradient, so the actual speed is increasing, and that's what's important to understand. And so the acceleration is positive and it's coming towards me. Acceleration positive and it's coming towards me. Right, so hopefully all of that makes sense, and I'm just gonna pause this and open a new blank sheet for the next question, which is question 8, saying sketch a typical velocity time graph. So we're next going to talk about the velocity time graphs. These were distance time graphs. And actually, before I do that, I haven't really answered the question yet. I've just been going on a rant on how the meaning of the graphs and how the gradient is the velocity, but I haven't actually answered the question very well. The question was asking how to calculate the velocity or the speed from a distance time graph. So I haven't really said it, and even though I've implied it, but I haven't really said it very clearly. So I'll just do an example here very quickly. If that's time and this is distance and this is our speed, if we know the value for the distance here, which is like 30 for example, and we know the time that goes by, which is maybe 2 minutes or 20 seconds, and so if the distance goes from 0 to 30 in 20 seconds, then we need to find out the gradient, right? So I said in the previous video that we're finding the gradient. So in this case it would be very easy. It would be the change. Delta means change, so change in distance divided by the change in time, or the rise divided by the how far along it goes, by the by the base of this triangle. So in this case it would be 30 meters per second. It's gone from 30 meters per second, from 0 to 30 meters per second, divided by 20 seconds, which is the time that it took. So that would be 1.5 meters per second would be the speed. So the velocity would be the speed would be the gradient, and the gradient would be here 1.5. You can calculate it between any 2 points, so you could do it from here to there, and then you would have to take this change in distance and that change in time, right? And since it's a straight line, if you did this for only this part here and that part, you would get the same gradient as you would if you did it with this one, with a big triangle. Okay, they're called similar triangles, and you would get the same gradient. You can try it out for yourself if you want. And so I'm going to go into velocity time graphs now. So the question says, this is now question 8. Sketch a typical velocity time graph. So let's sketch a typical velocity time graph. I'm gonna make a big one. Velocity time graph. So now, velocity is a vector, we said. So now we're gonna, instead of doing a speed time graph where this would be just like that, then we're gonna have to include this down here, because now we can get positive velocities or negative velocities. Now it matters, right? Because velocity is a vector, so then we have different directions. So if this is my origin, then things can go in a negative velocity with respect to where I'm measuring, or it can go in a positive velocity. That means, for example, the equivalent of this would be in a real life situation. If I'm here standing, if I'm standing there, then if I'm measuring that direction as positive, I could be measuring then this one as negative. So if I'm looking at what direction my yellow dog is going, then that's a very ugly dog, I'm sorry about that, at least with a tail. It could go in that direction or it can go in that one. So whatever it does in this direction we would call positive velocity when it's going in that direction, or when it's going in that direction it would be negative velocity. Okay, it doesn't have to do so much with the position, because the dog could be over here but it could be going in the opposite direction, and if it's going in the opposite direction then the velocity would be negative even though it's to this side of me, right? So it has to do, so this would be negative velocity and that would be positive velocity. Okay, so hopefully that makes sense, and I'm gonna go ahead and delete these dogs because they're quite disturbingly badly drawn, and go back to my graph. So the question says sketch a typical velocity time graph and point out all the important parts of it. So let's draw it ourselves. So let's say like this happens, and then maybe this happens, maybe here it just continues, and then you could have this, and then maybe that. Okay, so let's talk about what's happening here. So the questions are similar to the ones that we had in the previous graph. Like I would encourage you to ask yourself the same questions. What was the first question? It was, what is the y-axis represent? And in this case the y-axis represents velocity. Okay, so here and also here it's a vector, so the symbol matters, the sign matters. So what's happening, what does a rise in the y-axis mean? Well, a rise, right? So if this goes up or changes, a rise or a fall in the y-axis means changing velocity, right? The value of the velocity itself is changing, because here the velocity could be 30 meters per second, and here would be 0 meters per second, obviously, because it's on the axis, and then here would might be minus 40 meters per second, or it would be, well, being true to the scale, it would be probably same, right? So about minus 30 also, minus 30, and this guy here I'm going to delete because he's getting in the way, but we don't want to forget it's negative, so we'll say here that it's negative. Okay, so a rise or a fall or any kind of change on the y-axis then means a changing velocity, right? It means changing velocity, and it could be a rise or a fall, it doesn't matter, but just change in the y-axis here would be a change in velocity, and so therefore it just means an acceleration. It immediately means an acceleration. Any change will be an acceleration, either bigger than 0 for positive or smaller than 0 for negative acceleration. It can be either. So if the velocity is going down, if it's getting smaller, if it's going closer to the 0, then it's getting smaller, right? So here we have to be careful with what's happening. So if the velocity is getting smaller to the 0, it means the velocity is getting smaller, but not necessarily if it's going down it means that it's getting smaller, because here it's 0 velocity, and then it starts to increase. It's increasing in the negative direction, that's true, but that means it's just increasing in this direction here, right? It just means that the velocity in that direction is increasing. So it's really how close we are to the 0 here that matters in terms of the magnitude of the velocity. So if there is any rise or fall, there is definitely an acceleration happening because the velocity is changing, and if it's let's see what else we can ask about this. So we know that the y-axis is velocity, that a change in the velocity is going to be an acceleration. What happens if it's a straight line? Well, a straight line, what does a straight line mean on a velocity time graph? It means a constant rate of change, right? So if there's a constant rate of change of velocity, it's the same thing as a constant acceleration. Constant acceleration, right? So if it's going down or up, it means there is some acceleration, but if it's a straight line, it means it's a constant acceleration, or another word for that is a uniform acceleration, right? If it's a curve, then it's a non-uniform acceleration, right? So if it's not a straight line, if it's a curve, then we have a non-uniform acceleration. Now here, so let's analyze this graph in the light of what we've just been talking about. So here there's a flat horizontal line. What does a flat horizontal line mean? Well, if the speed is velocity is 30 to begin with and it stays at 30, it means the velocity is not changing. So this is constant velocity, right? A constant velocity means there is no change in velocity, so therefore zero acceleration. Okay, you don't have to write zero acceleration necessarily, but you have to know that that's what it means, definitely, and you would have to write this. That would be the important thing, the constant velocity, if you saw a horizontal line like that. But it also means zero acceleration, so you've got to know that, both things. Acceleration. Now this one is a change in acceleration, so sorry, a change in velocity, as you can see from the line that it's changing. So from, let's split it in parts. From here, so let's call this A, and this B, and this C, that's D, that's E, and that's F. From A to B, there's a constant velocity or zero acceleration. Then from B to C, there is a decreasing velocity. It's getting smaller and smaller and smaller, but it's with a straight line, so that means there's a uniform decreasing velocity, or uniform negative acceleration, or a uniform deceleration. Same thing, uniform negative acceleration or deceleration, until it gets to here, and here it's stationary or at rest, right? It's at rest because it's at rest means velocity zero, and the velocity here on the axis, this is where the velocity is zero, so therefore there it's not moving, right? It's completely still. So it's been slowing down. It was going here at relatively fast speed, then it's been slowing down until it reaches here, speed of 0. Then it starts increasing its velocity again, but in the opposite direction, in the negative direction. So if before the velocity was in that direction, then the velocity now is going to be in that direction. Right, so it's increasing velocity until it reaches here, and then so here this would be it's increasing velocity in the negative direction, so it's actually increasing velocity. If it's increasing, it's a positive, it's an acceleration. Acceleration in the acceleration, so positive acceleration because it's increasing, and it's just that the velocity is in the opposite direction, but the velocity in opposite direction, that's in brackets. You wouldn't have to write that down, but it's an acceleration because the velocity is increasing. Then it reaches here, and then it's a constant velocity again because it's not changing, it's like horizontal, so that's a constant velocity, negative velocity, right? Negative, so it's constant and it's going towards the left. And here look what's happening to the velocity. So just as a recap, a curve on a velocity time graph means then a non-uniform acceleration, but a curve in the distance time graph meant a non-uniform velocity, so constant acceleration, well, depending on the curve. That's hard to see from a distance time graph, but a curve here, it's a non-uniform acceleration. So straight line is a uniform acceleration, so this was uniform. Okay, so I'll see you in the next video for the next question.